Uh, Thanks everyone for the invitation to be here. My name is Eric Pahl. I'm presenting on behalf of myself and the authors, as well from the University of Iowa. We're a academic medical institution in the central United States. So first, I'd like to acknowledge some funding that we received for this through the National Institutes of Health and the Organ Procurement and Transplantation Network in the United States, as well as some collaborators locally in the state of Iowa. As many of you may or may not know, a little bit about organ transplantation and kidney transplantation. It's usually the most effective therapy for organ failure. Many patients, at least in the university or in the United States, are awaiting transplant but don't receive transplants before they die. This is due to particularly lack of organ supply, but also the lack of quality of assessment of the organs that are available. So the next few slides, I'll show a few of the statistics that we have in the United States, and largely in other countries as well. We have similar lack of utility of organs that are available. So that's kind of setting up for the prediction problem and motivation for doing this work. First off, in the United States, the number of organs that are authorized have been increasing dramatically, especially in the last 10 years. However, the number of organs actually recovered and the number of organs transplanted are fairly low compared to the organs that are actually authorized for transplant. And in the United States, we have a process for consent for organ donation after a person is deceased, and they have to authorize for consent first before transplantation happens. In other countries, it's a default where everybody consents, which I believe is a superior option. However, in the United States, you have to opt in. It's not a opt out for organ donation. So we have a very small amount of organs that are available because of that difference. But of the ones that we do have that are authorized, even fewer of them are actually transplanted. So we need to improve this. Obviously, we can transplant most or all of the organs that are authorized. So here's a few good circles that show the number of eligible deaths, the number of donors, and the number of transplants. These are the three internal circles. And then the true potential for donation that we have is a lot larger. Said differently, we should have about 37,000 potential donors instead of the 9,000 we actually have. So this is only 25%. 25% of what we have available today for transplant. So we believe that more organ offers will be authorized for transplant, and we need to reduce the wasted or unutilized organs that are available already. They're already consented, they're already available, however, they're not being transplanted. So we would like to build a model to aid the assessment of kidneys, to determine which kidneys are good for transplant and which kidneys are not good for transplant, because we know that retrospectively, many more of the kidneys that are discarded or not used could be great for transplantation. However, they are not used. And clearly that's not appropriate for the state of kidney disease in the United States. So we set up a clinical prediction setup here, and just a few of the terms that we'll be using. We're building a model that predicts kidneys that survive to a certain number of months after transplant. We're looking at 1 year, 2 year, and 3 year graft survival. That's the transplant survival rate. The model predicting it correctly, predicting a death correctly is a positive, and predicting success correctly is a negative. So those are the kind of the terms that we'll be using. And then we have our type 1 and type 2 error rates, or false positives and false negatives, where the model misses a good kidney or the model misses a bad kidney, which is the worst type. So the false negative rate is clearly something we want to minimize the most. If we're going to predict that a kidney transplant is good, it better be good and survive to the extent that it does. So this is so we built a survival duration model for 12, 24, and 36 months. And this is largely based off of previous work with the Kidney Donor Risk Index back in 2009, which is a Cox proportional hazard model. We used all of the same data from 2009 to design the environment and test our model. And we used the same database that was used during that time with the Cox model. This was in order to set up an experiment that was as close to the original experiment as possible, and leveraging a few different models that could help, specifically random forests. And that's the one that I'm going to talk about today, and it's the one we presented in our paper. So there were a few steps for pre-processing that we did in order to make our environment as close as possible to the development of the Kidney Donor Risk Index. And what we did beyond that was we used a model with machine learning called the random forest, and we added the donor and recipient characteristics that were the same characteristics that were available in the previous model. And then obviously we're doing the graft failure at 12, 24, and 36 months post-transplant, only with the data that are available before the transplant happens. So this is our task to do that, so that in future case, we can perform a reasonable prediction so that we can transplant more organs more confidently. A few things about the random forest with this audience. I think we can perhaps go through this rather quickly. Many of you are already familiar with the random forest model. It's an ensemble of decision trees that are built from bootstrap samples of the entire sample population, which I described in a few slides prior. A square root number of the features are selected for each tree. So each tree within the random forest operates on only a smaller subset of the study population. And then each of the trees makes an independent prediction, which is then aggregated together to vote on the prediction of the ensemble or the combined model. So some trees may vote that, or based on their training and the subset of data in that tree, or the features that were selected in that tree, they may say, well, this organ could be, this organ is going to fail. And some may say this organ will be successful. And you take 1,000 trees and the majority vote carries over for the end result for the prediction and classification. And that's just in one case, and then you do that for all of the testing data. So a few cases that we did here, we had 3 classes of model that we discussed. So the Kidney Donor Risk Index is the KDRI at 12, 24, and 36 months. And then the random forest with only donor variables, and then the random forest with the donor and the recipient variables, which we think is very important to have, because the recipient is the patient that's going to be living for those 12, 24, and 36 months. And to take in the factors only from the donor is greatly limiting our opportunity for prediction. And we seem to be correct in that hypothesis, because with the addition of the recipient variables and the flexibility of the random forest compared to the Cox proportional hazard model, we were able to achieve higher area under the ROC curve. And I'll go into more detail there. Here is the experiment with the multiple number of trees. multiple different numbers of trees for the random forest algorithm, you'll notice that as we increase the number of trees in the algorithm, we reach sort of a maximum cross-validated area under the ROC curve, or AUC. And of course, kidney donor risk index is not a tree algorithm. It's the Cox proportional hazard algorithm. It does not change whether it's a separate experiment that's been displayed on this graph or on the table figure for purposes of comparison directly. It did not change based on the number of trees because the algorithm does not use trees. So I go into more detail about the figures in the paper, and I suggest everybody go and read that if possible. The one that I want to highlight here is the difference between the ROC curves for 36 months between the random forest with the donor recipient and the KDRI. You'll notice that it's not the random forest has a higher AUC, obviously, as we saw before. However, the margin of improvement in sensitivity and specificity are not consistent throughout the ROC curve. And specifically, I'd like to highlight 10%, or the final 10% or 90% sensitivity, which is the clinical threshold for the utilization of the model in the clinic. So we did this with Dr. Alan Reed, who's the last author on the paper. We're supporting a clinical trial with multiple models in the future, and a 10% sensitivity or a false negative rate is the bar for utilization of any models in the clinical decision-making process. So from that standpoint, the rest of the receiver operating curve is less exciting than 10% and above. The false, or 10% or less, 90% or higher sensitivity. All saying the same thing. But when we have the false negative rate at 10%, which means that's the rate of the worst outcome. This is the rate of the algorithm saying that it's going to be a good kidney. However, in reality, with the test data, it shows that these kidneys did not perform well. And if we're making a judgment for transplanting a patient and it doesn't turn out well, the transplant center is then liable for that result. So we don't want this to happen very often, and the 10% failure rate is the standard of care in the United States for outcomes at 1, 2, and 3 years for kidney transplant. So that's acceptable. And just in comparison here between the KDRI and the other models, you can see that we perform the same amount of the false negatives in this bottom row. And this is expected because we've selected the false negative rate to be 10%. So they're all the same, or as close as, as close as as we were able to get in the experiment. However, you'll notice that with the same number of false negatives, we're actually improving our classification of true negatives by 26% compared to the kidney donor risk index. And you can see that even in the random forest donor column, it's by 2%, which is a small amount, but it still amounts to 200 more kidneys here. But in the case of using the random forest with the donor and the recipient, we get 26% more kidneys than in the case of just the KDRI model. So this is without sacrificing any prediction risk. We can actually achieve a little bit more transplants with the same risk level. And in this subtable B, I've just highlighted that as well. and actually the total number of additional kidneys that we could achieve in this population, or during the study period, was another 2,148 kidneys that would be classified correctly with a 3-year graft survival. And you'll notice at different rates of the false negative, you have different numbers of additional kidneys that are transplanted correctly, and it happens that 10% happens to maximize that by chance. So this slide is the same slide. The next thing we wanted to do is make sure that our survival was extended beyond 36 months. We designed the clinical experiment or the prediction on 3 years, because 3 years is an important milestone for kidney transplant. However, in many cases, we want the transplant to last a lot longer. So we want to make sure is when we follow up with these patients, and in the case of using data from back in 2009, we have a much longer follow-up available for all these patients, which is kind of the benefit of the data that we have available from the Organ Procurement and Transplantation Network in the United States. All the follow-up data and when patients fell out. So in this case, we were actually able to track the patients for another 10 years after the original study from Rao for the kidney donor risk index. And we were able to make our classification into 2 groups. So we have the red line for the kidney donor risk index and the blue lines respectively for the random forest using the donor and the recipient variables. In the case of predicted success, our survival probability across the population is actually higher all the way out through 20 years or more, compared to that same group that was predicted by the kidney donor risk index. And in fact, in both cases, the p-values for each of these cohorts, prediction cohorts, are statistically significant, showing that not only can we predict more successful kidney transplants at 36 months, but those groups that we've identified include more transplanted patients, more successful outcomes, and the longevity of the matching and the longevity of the survival maintains throughout the rest of the patient survival through the end of the follow-up that we had available, which was like 20+ years. So that's kind of very interesting. So sort of our future work and the next steps here is to actually implement this in the point of care. So we designed a mobile application that we're going to take to the next step to actually have a prediction available for the donor and the recipient at the time that the donor is available. And as I discussed before, some of the limitations on organ transplant, I did not discuss this before, but the time it takes to make that decision is extremely limited because organs don't last very long outside of the body. And we have lots and lots of people that need to be matched with those organs appropriately with our federal allocation system in the US. And it takes a really, really long time, maybe 30+ hours to get that kidney to the right person. So as much as we can make a faster, better decision, we can do that. And we think that this will be a good application in the clinic for future work. So thank you for your attention.